Hello everyone. First of all, I would like to thank IGRG for the award. It is really a great honor. This is my fourth participation at IGRG. I first participated at HRI, Harishchandra Research Institute, where I did my PhD, probably in 2011, where it was held at HRI. And after I joined IMSC, I have been taking part in this IGRG schools or conferences every year. I'm really happy to be back here this year as well. So the theme of this conference is the tensions in the standard model of cosmology. I'm going to talk about that. And I'm going to present a new technique to solve this solve this problem of the standard models in cosmology that can be anomalies, that can be tension between different data sets. So basically, my talk title suggests that, for example, if we have tensions, if we have anomalies, if they are not systematics between the data sets, that leaves one window open, that is that we have certain hints of new physics. So the talk is based on how to search for beyond standard model signals in the data. All right. So what is the standard model of cosmology? I assume that Eleonora and other speakers of this conference has already spoken about it, but just in a nutshell, I would like to stress again that in the standard model of cosmology, we assume or we accept that the theory of gravity is basically given by Einstein's theory of gravity, g mu nu equal to 8 pi g t mu nu. The metric is homogeneous and isotropic at large scale. This is an observational artifact that we have found. The constituents of the universe are baryons, cold dark matter, a dark energy described by the cosmological constant lambda, and for initial condition, this is very important, I will be basing my talk mainly here. The initial condition is given by a complete slowly rolling inflaton field, a scalar field, which gives a form of primordial power spectrum or the spectrum of the primordial perturbations given by a simple power law, just given by one amplitude and a spectral tilt, okay, two parameters. And combining all of them, we call it a baseline. So whenever you read a paper, Planck paper, let's say, Planck satellite paper, so you will see this word baseline. So by baseline, we mean that we have a lambda CDM model of the universe with a power law form of the primordial power spectrum. Now, how do we determine the standard model parameters? Is by cosmological observations. We have a model, we get the prediction from our model, our favorite models, and then we compare them with the data. So at high redshifts, we have cosmic microwave background, that is the best probe for the primordial physics, and that is the best probe for understanding the constituents of the universe as well. At low redshifts, we have supernovae, galaxy clustering, and lensing as well. And there are many other probes, I am not going to talk about those. So what are the anomalies and what are the tensions that are there in the present in standard model of cosmology and between different data sets? So when I say anomalies, I refer to the fact that if we have a model and if there is a particular data set we are trying to fit the model with, if there are certain parts in the data the model is not able to describe, that I call as anomaly, and where we try to find hints for new physics as well. And by tensions, I say that let us say we have a standard model and we have two data sets. We get the constraints of parameter A from one observation, and we try to get the constraints on the parameter 8 from the different observation. They do not match each other and they do not have a statistically significant overlap between the error bars. So that is what I call tensions. Okay, so there are anomalies and tensions. So in CMB, one of the most intriguing anomaly is the lensing anomaly. So you know that the structures, the large scale structures lens the CMB. This is a weak lensing effect, and you can actually calculate that using the lensing calculations given by the GR. So what we find is that from observation, if we just try to fit the standard model with the data, we find that the acoustic peaks in the CMB appear smoother. Okay. So, this is a particular cartoon picture of the lensing, and these are the constraints. So, what you can see that if you have the temperature polarization constraints on the lensing, if we, okay, A lens is not a real parameter, we just multiply A lens as an ad hoc parameter. For consistency, it has to be 1. If it is consistent with the standard model, it has to be 1. But as you can see, nearly at 3 sigma, it is not consistent to 1. Okay, it is higher than 1. So, if it is higher, then your peaks will be smeared more. So, that is what we see in the acoustic peaks of the Planck CMB observations, and they are more prominent after L equal to 1000. Solution, there has been solution proposed by, okay, it has not been proposed by Planck as a solution, but it's this degeneracy was also discussed in Planck, but Eleonora's paper, Eleonora et al.'s paper showed that if you have a closed universe, you can solve this problem. So, you can have a omega k, the curvature density less than 0, and then you can have A lens equal to 1. What are the problems? Okay, we should be happy with that, right? The problem is that problem comes later as well, but what are the if I want to describe what are the problems, I have to show you another one, the tensions that are there in the data sets. So, if you have indirect measurements of the Hubble parameter, you know what Hubble parameter is, and the indirect measurements show the Hubble parameter always comes with a Hubble parameter determination which is lower, okay, nearly 67 or something like that. If you have a direct measurements like these, you can also find this in this paper, they always tend to be gathering in the higher direction, nearly 73 or something like that, as you can see. Okay, and two most precise observations, direct and indirect. For indirect, I am referring to Planck CMB, and direct I am talking about Riz et al. HST observation. They are more than 5 sigma apart from each other. There are other tensions as well. The S8 tension or sigma 8 tension, it is basically related to the structure formation. If you basically calculate the sigma 8 parameter from large scale structure, lensing, galaxy correlation, etc., that value comes out to be lower than the what you get in the Planck CMB data. Okay. There is another one internal inconsistency that is there in the Planck SSE measurements, but I am not going to talk about that. Okay. Now, I said that in this paper they have said that this omega k lower a closed universe can solve this problem, right, but it aggravates other tensions. What happens is that if you have a closed universe, your H naught contour or your H naught constraint will go down, it will be like 50, and as I said, the direct determination of H naught wants it around 73. Okay. So, the difference between 67 and 73 becomes 50 and 73. There is another problem as well, this sigma 8 and omega matter, for example, here it goes in this direction. So, there was some tensions around 2 to 3 sigma here, but now if you have omega curvature, then it moves apart, all right. Now, another thing that you will not find in the data, that it has problems in initial condition. If you have a curvature, it will have problems in starting inflation. So, if you just try to solve a scalar field equation with a curvature density, you will not be able to start the scalar field rolling slowly towards the bottom of the potential. Now, what are the solution to the H naught problem, the Hubble tension, right? There are many solutions that are proposed, for example, early dark energy, emergent dark energy. This is the early solution, early universe solution. This is a late universe solution. There is this negative cosmological constant, scalar tensor theory, early modified gravity, other extensions to the standard model. Some people said that it can be systematics in the H naught measurements, the HST, and some other people said that there can be systematics in the Planck CMB data itself. All right. So, these are basically the candidates of the new physics up to 6, and 7 and 8 are saying that there is something happening either in one data or the other data or both. Okay. Now, what we try to do is that we try to find a common solution for that. And what we need, just as I described, what we need in order to have a common solution, just let us have a simple recap, is that we need a power spectrum. We try to find a power spectrum. We try to get the initial condition, and we are saying that this might be the candidate for the new physics. Now, we are saying that a power spectrum that can mimic the lensing. We are saying that that excess lensing is not an artifact of a gravity that is not described by the Einstein's gravity. It is simply Einstein's gravity, but your initial power spectrum is different. We want also a spectrum that prefers a flat universe. We also want a spectrum that prefers higher H0 than baseline in the CMB, and we want a spectrum that prefers a lower S8 than baseline in the CMB. All right. You remember the main problem that comes here is basically with the Planck CMB TT data and the standard model. So if we rewind a bit, so as I said that how to, as my talk title suggests, that how to search for beyond standard model signals. So this is one of the approaches, that top down approach, and I am going to discuss the bottom up approach later. We try to reconstruct the primordial power spectrum. Okay. This simple data analysis approach, we say that there is data, we say that the data is at the top. Now we try to deconvolve the data from the data, the primordial power spectrum, because the primordial power spectrum and its convolution with the transfer function gives you this cosmic microwave background anisotropy power spectrum, right. So we have the data like this here, and you have a transfer function kernel. You iteratively solve it and try to find the shape of the primordial power spectrum. Of course, this looks messy, and you have to do lots of smoothing techniques, etc., in order to understand what are the places or what are the scales that where you can have new physics. In this paper, we showed that actually the reconstruction, the features in the primordial power spectrum can mimic lensing in 2014. Okay, you can see that these are the lensing effects, and the primordial power spectrum can indeed mimic lensing to the whole lensing to some extent, not completely. After that, we also tried that asked the question that can we solve the H0 problem with a primordial power spectrum. So we said that okay, what will be the primordial power spectrum if we fit to the Planck data, gives as good as fit to like the standard model, but comes with a higher H0. So this is the form that we got. Of course, you can understand that this form is very complex. Okay, it is nearly impossible to get this type of form unless we make it much more simpler. But it does our job. It actually comes up with a very high value of H0 and the lower value of sigma 8 and omega matter. So it basically falls on top of it. So this. So what we found is that if you solve H0, you solve the sigma 8 problem as well. In Planck paper 2018, the version 2, which came in 2019, I guess, they showed that this type of primordial power spectrum can mimic lensing. So which we basically showed here. So they found a form of it, and they showed that this is the form of the primordial power spectrum, okay, that can mimic lensing. So we try to find the spectrum, and we call it one spectrum, and we assume that the excess lensing is actually coming from a primordial signal, and we treat the best fit of the baseline. I already talked about the baseline, right, standard model, plus the A lens extension, that means the lensing amplitude extension, best fit to the Planck TT data as the input spectrum. I am not going into the data analysis detail. We basically subtract the lensing effect, and then we say that residual excess lensing effect is there, which corresponds to the 10% excess lensing, and we are calling that is coming from the primordial power spectrum. Okay. Now, we reconstruct the primordial power spectrum using that. What we find is that we find a very simple shape of the primordial power spectrum with simple oscillations. Why it is simple? Because it is sinusoidal and it is transient. You can basically mimic with a power law envelope. Okay. Now, when we use this one spectrum and fit the data, what you find is that your A lens parameter, the consistency parameter, becomes 1. And it actually, why I said that it mimics, because if you see the distribution of chi square, it actually falls on top of the A lens chi-square, okay, this A-lens extension of the chi-square. So that means that it says that it actually replaces the A-lens completely. You do not have to use A-lens. Now of course it comes with a many number of parameters, but at least we can physically motivate these parameters, while A-lens cannot be motivated, not from also modified gravity as well. You need, we do not know which combination of the modified gravity can give this type of A-lens. We just fit our data with that power spectrum, and we find that this omega k that was less than 0, now 0 becomes consistent at 1 sigma. Again we see that the chi-square CMB falls on top of the omega k contour. Okay. So how do we bring back the cosmic concordance? So this was the Eleonora's paper. So this is the plot if we do not, if in the standard model plus A-lens plus omega k. Now if we have reconstruction plus A-lens plus omega k, your 0 and 1 line actually is at the border of 1 sigma. So it actually solves your discordance problem. It reduces the H naught tension. At the same time, what we find is that the standard model H naught is nearly 67, it becomes nearly 70 or something like that, or maybe here it is 69 or so, something like that. What happens to the S8 problem? S8 goes back. While omega k, you have seen that S8 or sigma 8 omega matter, it was going away from the large scale structure contour from KITS 450, but now it is coming closer. So there is a complete agreement with the large scale between the large scale structure observation and the Planck CMB observation. All right. So this is the S8, for example, the one dimensional contour. I am not going to that. Okay. In age of the universe as well, we found a little bit better consistency compared to the standard model, that globular cluster had a 1 sigma type inconsistency, but 1 sigma inconsistency is nothing, but this actually reduces it anyway. We did not start with that, but we found it anyway. So what one spectrum gives us? So one spectrum that we have is to mimic lensing. Yeah, thank you. One spectrum is to prefer a flat universe. This one spectrum prefers a higher H naught than the baseline, and at the same time the one spectrum is to have a lower H naught S8 than the baseline. Okay. So this is a common solution to almost all the problem. As I said, H naught is reduced, H naught problem is reduced, it is not completely solved, but it is but if you have one spectrum, it actually does not aggravate one problem and reduces another problem. I should advertise another thing, that all the other other models that I had discussed here, if you want to solve one problem, for example H naught problem, your S8 problem gets worse. So in most of the cases, if you have a model that goes for a higher H naught, it will also go for a higher S8. Okay. So if you are basically making one problem better, you are making the other problem worse. So the next question comes obviously, that can we parameterize such spectrum? Of course. As I said, with a sinusoidal decaying sinusoidal oscillation, we can achieve it. Now this can come with several parameters. This has 5 extra parameters, and we found that with 5 extra parameters, the Bayes evidence, it gives us a better fit to the data, but the 5 extra parameters is not good, because your prior volume increases, so you get penalized. So you do not, so the negative number means it is not preferred over the standard model. Here also it is very close to 0, so it is as good as the standard model. It says the restricted spectrum is given by this with 4 extra parameters, which is much simpler than this one. It looks much neat as well. If you use the HST prior, then you get much better evidence for these models. For example, this gives you a strong evidence for the model 3.4. Okay. How we say that this is actually, this one spectrum solves this problem? As I said, let us have the contour plots again. So it has a negative correlation with A-lens. If it goes higher, goes in a higher direction, it will drag lensing amplitude lower. This is what we wanted. If we have the amplitude of the oscillation higher, the omega k goes higher, goes to the flat universe. If we go for higher alpha 1, means that higher amplitude of the oscillations, omega matter reduces, S8 reduces, but H naught increases. Okay? So, one spectrum solves all these problems. We tried to test with different combination of the data sets with and without HST, with the dark energy survey observations, etc., and we found that it is consistent with almost all the data sets. It has another signal in the large scale structure. If you calculate the correlation functions, you should get a peak and a trough in this region around 300 megaparsec. So, we need better large scale structure observation to see this kind of peak if it actually exists. Now, the second part, I will speak only for 3-4 minutes on this one. So, I talked about getting the primordial power spectrum, right. This is one of the approach that you from the data you use some deconvolution, a top down approach in order to get the primordial power spectrum. The thing to ask is that, okay, it can be parameterized, can it be obtained from a phenomenological model, let us say the model of inflation? The answer is yes. We try the Hubble flow functions. So, let us say this is the Hubble flow function that gives us a nearly scale invariant power spectrum given by 2 parameters, amplitude and tilt. Then we change this flow function with we modify this flow function with this kind of modification, a cosine and then a decaying factor. Okay, I am not going into the thing, into the data analysis. What we find is that whatever we found in one spectrum, our model of inflation is actually getting all these peaks at the same place. Okay? So, there is a consistency between the top down approach and the bottom up approach. So, this is the convergence of the top down approach and bottom up approach, where you can identify a model and you can give a coherent picture of the universe. So, we found that it is consistent with Planck, temperature, polarization and lensing, and with the Hubble Space Telescope observation as well. We cannot say for sure that this is the model of the universe, but with the CMBS4 type surveys we will be able to say, because the A lens and our model has this type of difference. So, they are out of phase in the polarization data. So, you can see that these are the error bars of the Planck data, but CMBS4, this band represents what the error bar you can expect from CMBS4. So, you can understand that this much difference can be easily identified by a CMBS4 like observation. All right. We can reverse engineer the potential of the inflation from the Hubble flow function, and what you can find is that we find that you need a near first roll. The inflation has to be through the slow roll, but there is an intermediate departure of the first roll only for 0.5 e folds. That is only necessary, and this is what you find, that this part is necessary in order to solve these problems. So, we find strong support for an intermediate first roll for 0.5 e folds of inflation. So, let me summarize that anomalies and tensions within and between cosmological observations are correlated. So, it is not that you need to have different models in order to solve different problems. You can have one common solution, that is the one spectrum. Okay? And we find statistically significant preference for an intermediate fast roll, as I said. This candidate has strong signatures in CMB polarization and large scale structures at particular scales, 300 megaparsec. We can identify this type of oscillations if they are present. What we can expect is that, okay, the thing is that I should confess that our solution does not solve all the tensions in cosmology, but it seems that it is the only solution till now where the shift in the parameters are in the right direction to resolve the tensions. It has a physical origin. Okay, it is not an ad hoc parameterization like A lens. Lensing likelihood and okay, so there are certain data sets that are reducing the significance of our model, but not that much. But given the origin and other correlations, for example, if we have 3-point correlation function, not the power spectrum, but let us say we can calculate the bispectrum and compare with the Planck data, we can understand more about the models. So, right now we are doing this, and we hope that the results will be out soon, the primordial bispectrum analysis for these models with the Planck data. So, with that I would like to stop. Thank you.
Thank you for that. We have made up a bit of time. One or two questions. Yes.
Hi, Dhiraj. Thanks for the nice talk. So, can you give us a why in the end it solves the problem? I mean, you did something at the very small scale in the power spectrum, but what is the general intuition that in the end both sigma 8 goes down and this H0 gets resolved? I mean, what is happening in the end?
Okay, so let us go back to WMAP era, where actually things were consistent. What Planck did is that Planck came up with a few more acoustic peaks at the small scales. So there the problem starts. So people have showed that Planck before L equal to 1000 and after L equal to 1000 there are significant differences. But we cannot say that the differences because Planck is more accurate. So we cannot say that WMAP is right and Planck is wrong. So the main thing that lies is at the small scales, and lensing is a small scale phenomena, intermediate to small scale phenomena. Lensing doesn't affect lesser than L equal to 500 or L equal to, let's say, 800, because WMAP lensing was not that much prominent, right? In Planck it became prominent. So if there is some problem in lensing, there is a problem in the at the small scales. Now the H0 problem, what H0 does, it shifts the acoustic peaks, right? This model says that you do not have to shift the acoustic peaks omega k, that also shift the acoustic peaks. That is why omega k solves this A lensing problem, but in order, so all the acoustic peaks get shifted to a particular scale.